Came back to let you know you're not alone. And in this turmoil, I will direct you where to go. You're not alone. I've been here twice before, and I felt what you felt years ago. And in this turmoil, I will take you where you need to go. What your heart needs now is a brand new place to travel.
Alright, ladies and gentlemen, we have for you today notes on inscribed angles. Okay, that little video was just on shooting some pool, which is kind of interesting. It's a lot of geometry, all of that's involving angles, so forth, and there's spheres for the balls. So just thought it was something to kind of get you going this morning. But let's take a look. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. All we're saying is this. Okay, as long as it goes all the way back, all right, is what we're looking for here. That would be your inscribed angle. Now, the intercepted arc is the arc that lies in the interior of the inscribed angle, right here. Okay, that's your intercepted arc for this particular case. So the measure of an inscribed angle for theorem 10.8, if an angle is inscribed in a circle, then its measure is half the measure of its intercepted arc. So if I had myself a circle drawn, and let's say that I tell you this is 80 degrees. To find the inside, all we do is take this number and divide it by 2. 40 degrees. Now it works in reverse also. If I tell you this is 10 degrees, alright, and I want to know what this angle is, or this arc, double it. Okay, 20 degrees. So it's either half or double it, depending on where you're going from. Okay? Let's take a look and see how easy this really is. Only thing you have to ask yourself is, are they telling me the arc, or are they telling me the inscribed angle? If it's the arc, divide by 2. So in this case, it's the arc. So to find the inside, just take 140, divide by 2. 70 degrees. Okay? So for part B, I'm checking out again. Here's my inscribed angle. So instead of dividing by 2, I have to take 80 and just times it by 2. 160 degrees. Okay? Pretty simple, right? Good. Part C, arc RVT. Okay. Oh, sorry. They want us to find this particular arc. They're telling us the inside angle RST is 91 degrees. So 91 times 2, 182 degrees. Okay. And lastly, this one's kind of interesting. They're telling us this. It goes out to here. So I want to find this arc first. I'm timesing this by 2. So that would give me 76 degrees. But then I want to find angle A, so I'm just going to go back again and divide it by 2. So 76 divided by 2. Once you know it, it's the exact same thing. So angle A is 38 degrees. This problem right here leads us to our very next theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. Can you see up here how these both went to the same arc on the outside? Therefore, angle A and angle D must both be the same. We'll get used to that as the year goes on. Okay. Very, very good. So if you're looking for an example for this, look no further than part D. Okay. Little star right here. If all the vertices of a polygon lie in a circle, the polygon is inscribed in the circle, and the circle is circumscribed above the polygon. Real quick little side picture. Something kind of neat. I can draw a bunch of points on this circle. So I do 5 right there. Now I'm going to go ahead and connect the dots. Okay, now, anybody know what a 5-sided shape's called? That would be a pentagon. Okay, so this pentagon is inscribed in the circle because it's inside of it and all the endpoints of it lie on the circle. Okay, or you could say the circle is circumscribed about the polygon. Either way you look at it, you're still okay. Right? Now we're going to use this because it's going to help us out with theorem 1010. If a right triangle is inscribed in a circle, I'll show you what that looks like. Okay. Then the hypotenuse is the diameter of the circle. If you ever have a right triangle drawn in a circle, this side right here has got to be your hypotenuse as well as your diameter of your circle. So it's two things. Okay. Conversely, if one side of an inscribed triangle is a diameter of a circle, and the triangle is a right triangle, and the angle opposite diameter is the right angle. So the angle across this will always be your 9-degree angle. And there you go. Okay. Which helps us because if we know it's a right triangle, then we can use some theorems. Almost finished here. Pardon me. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. This is a good one too. Please keep in mind all of these theorems I'm going to give to you, so you do not have to memorize them. So if you wonder why I'm going kind of fast through them, it's kind of because you're going to have a sheet that has all of these written down. Like you'll have theorem 1011, theorem 1010, everything. Okay. What this states, I'm going to call this 1, 2. If I ever have a quadrilateral drawn inside of a circle, angles across from each other are supplementary, which means they add up to 180 degrees. And if this is 3 and 4, I can say angle 3 plus angle 4 adds up to 180 degrees. Okay, so we're going to use that again down here. All right, number 3. This is the same picture as before. This is an inscribed angle. So 2x plus 1 has to equal half of 96. Okay. Now, if this confuses you seeing it like this, then what you can do is just take 96 divided by 2, 48. Subtract 1 over. Divide by 2. 23.5. There we go. Again, don't panic when you see decimals. It's okay. If you plug it back in, you should find that this equals half of that. Okay, it should equal 48. This one over here is like a spotlight problem. I don't know. It's just it sticks in my head. I like to think to myself too that these are the bat singles. Batman. I'm totally not kidding when I say I think that's what it stands for. But anyway, I could set these equal to each other. 2x minus 7 equals x. I can add 7 over. I can subtract x. X equals 7. Okay? Looking good. Last two. You see how both of them are going out to your spotlight? Or, sorry, rather, they're going out to your intercepted arc. Okay? So this angle goes out to it as well as this angle. Therefore, I know these two must be congruent. So what I can do is just say 3x equals 2x plus 13. I can subtract 2x over. X equals 13, right? And finally, this is your, I don't know, it's a little bit oddball out, but it's not too bad. This is a quadrilateral. How do I know it's quadrilateral? 1, 2, 3, 4-sided, okay? So we just learned in Theorem 1011, opposite angles have to add to 180. So back down here, I have opposite angles, 3x minus 8 and 5x plus 2. Add them up. So 180. Combine like terms. Okay. Add 6 over. And then 186 divided by 8. 16. 8 goes into 26 3 times. 8 goes in there 2 times. 8 goes in there 5 times. So 23.25. Okay, a little bit of long division there. So, alright guys, hopefully this isn't too bad. Just remember, inscribed angles are half. They're different than central angles, okay? Central angles are the same. And again, as always, very, very importantly, keep this in the back of your mind. Good luck. We're all counting on you.